Hey folks, welcome to the worksheets. We're going to go through the first worksheet for solutions. Shouldn't be that difficult. Explain why water's polar. Well, water's polar partially because of the shape of water. If you remember, oxygen looks like this and it bonds off to water like this. We have a 105-degree bond angle here, and we've got a couple of naked electrons up here. A couple of naked pairs. And these naked pairs end up having a slightly negative charge, and that's the way we draw this, right? We have a slightly negative charge up here, and as a result we have a slightly positive charge down here. Now, hydrogen doesn't go and steal the electrons from oxygen. Oxygen doesn't steal the electrons, but they do spend more time up here by oxygen. So they leave a slightly positive charge behind them because electrons are negative. So the electrons spend more of their time with oxygen. So you get a negative end to your molecule up here, and you get a positive end down here. So you do have a positive and negative end to your molecule. And that's why water's polar. Now, because there is a large difference between oxygen and hydrogen, there's a large electronegativity difference. The electrons spend significantly more of their time near oxygen than they do near hydrogen. So this creates a very polar bond. So it creates a very polar molecule. All right. So knowing that those bonds are very polar, and that water is very, very polar, if we remember, we have fluorine and oxygen and nitrogen. If any of those are bonded to hydrogen, we create something called a very polar bond, which introduces hydrogen bonding. So, for example, when we have water, which is H2O, the oxygen has a significantly negative charge and the hydrogen has a significantly positive charge. Right, so what happens is it attracts another water molecule. Hydrogens are off on the other way. And this attracts a water molecule, so this oxygen, which has a negative charge, is attracted to that hydrogen. All right? And we call this thing right here, which is simply an attractive force, but a very strong attractive force, between this molecule and this molecule. And we call that dotted line a hydrogen bond. Again, it is not a hydrogen, it is not a bond, it is simply an attractive force. But it holds these things together. So typically when you find small molecules like this, small molecules tend to be a gas at room temperature, but water's not. And water's not because of these strong hydrogen bonds that exist between the water molecules. Again, these are very strong attractive forces. So how is hydrogen bonding responsible for the high surface tension and low vapor pressure of water? Well, when you think about the surface of water, you're going to have, there's no way to draw this on a two-dimensional screen, but okay, you've got oxygen to hydrogen over here, and you've got another hydrogen. Again, we're talking about hydrogen bonding here, all right, where this hydrogen and this oxygen have an extremely attractive force between them. Now this is all in the plane of the water, in the top of the water. And so now we've got another oxygen that's attracted to hydrogen, like that, and more oxygens that are attracted over here, etc. Okay, and all this is in the top plane of the water. And then in addition to that, there are oxygens that are under the water, and hydrogens, of course, that are under the water, that are pulling down on these guys with more attractive forces. So not only is there an attractive force that's pulling everything together, all right, so we've got different molecules here, and they're all being pulled towards each other. They're all being attracted towards each other, and they're all being attracted down into the water. All right, so as a result, since they're being attracted down into the water, then they're very less likely to leave. They're very less likely to evaporate. Right, and they create almost what you would call a film on top of the water, and that's your surface tension, and that's why water, so you get two things, you have surface tension, and you have the fact that the water is not evaporating as rapidly as you would think because there are other molecules pulling them down. Again, the hydrogen bonding is all responsible for this because these are the strong attractive forces between the water molecules. Okay. What's a surfactant and how does it affect the surface tension of water? We talked about a surfactant in that it disrupts the hydrogen bonds. It disrupts those attractive forces that pull this molecule towards that molecule. There's your oxygen, there's your hydrogen, there's your hydrogen. So for whatever reason, it's disrupting this attractive force, which we call a hydrogen bond. And something that does that, for example, is soap. So it will break up surface tension because it breaks up some of these hydrogen bonds by getting in the way. And that's what soap does. Okay, so a surfactant is something that, that disrupts the surface tension and disrupts the hydrogen bonds between the water molecules. Okay, so why does water have a relatively high boiling point and a relatively high heat of vaporization? In other words, why doesn't it boil at a lower temperature like other small molecules? Again, it is the same thing. You have a water molecule, you have all these water molecules. Not only are they attracted to each other up here, but they're attracted to other water molecules down below them. Okay, and since they're attracted to water molecules down below them, okay, they don't want to leave. So that's why they have a relatively high boiling point. What's holding them there? It's all of those hydrogen bonds. So here's water with hydrogen up here, and it's attracted to another hydrogen down this way. Okay, and you create this hydrogen bond. So guys, it's all about hydrogen bonds. That's what everything is. Okay, and that's what gives water its relatively high boiling point. Okay, what's the difference between the structure of liquid water and the structure of ice? And how does it explain why ice floats on water? Well, think of it this way. All right, let's say that you go into a room and there are bunches and bunches of people. The room is extremely crowded. Okay, and every person is standing there. This is a top view of a person. That's their head. And out coming this way is their arm, and out coming that way is their arm as well. All right, now let's think of all of these people in a room. Right, and they're all milling around and moving around. And when they move around, it's entirely possible that you could have another person who does this. All right, and then there'll be a person who does this with their arms out that way. And then there might be another one who's in like this. All right, and anyway, but they're constantly moving. So there's constant movement in this room. Okay, but then let's think of something where we go into the room and we say, okay guys, for whatever reason we're going to go and we're going to set everybody up so that everybody is facing so that their arms, so that their hand is on the shoulder, is on the head of another person. All right, so everybody has to line up like this so that their hand is on the head of another person. All right. Well, but you can't have two people going to the same head. I mean, you can make all sorts of rules. But anyway, bottom line is you line up like this. Well, notice how this takes up more room than everybody milling around. Right? Because you are creating a structure and everybody's at arm's length from everybody else. Whereas over here on the left, that's not always true as people move around. Well, the same thing is true for water. This is liquid water over here. And this is solid water or ice. Right? When ice forms, it forms this thing where oxygen and hydrogen, which is at the end of each arm, right? They're reaching out and they're pushing away from each other, and these hydrogen to oxygens are attracting. So you end up with a crystal structure. Now, when you do this in 3 dimensions, what you find is that there are holes that are created in this crystal structure. So the molecules are holding together so they are not moving around. They're not jostling around. And we create these holes inside inside this lattice work of molecules. And the question is, what's inside that hole? And the answer is there's nothing inside that hole. It's a vacuum. There's nothing there. So as a result, this solid is bigger than the liquid. If the solid is bigger than the liquid, that means it's going to float because it's less dense. There are less molecules per cubic volume. All right, so it's going to float. So that's why ice floats on water, and that's and hopefully that makes sense to you. All right. That's it. Enjoy your afternoon. Have a great day. We'll see you in class. Ask us if you have questions. Take care.